For section 2, we are looking at electrolytes and non-electrolytes. You'll be able to identify solutes as electrolytes or non-electrolytes. Solutes can be classified by their ability to conduct an electrical current. When electrolytes dissolve in water, the process of dissociation separates them into ions, forming solutions that conduct electricity. When non-electrolytes dissolve in water, they do not separate into ions, and their solutions do not conduct electricity. To test solutions for the presence of ions, we can use an apparatus that consists of a battery and a pair of electrodes connected by wires to a light bulb. The light bulb will glow when electricity flows, which can only happen when electrolytes provide ions that move between the electrodes to complete the circuit. In water, strong electrolytes completely dissociate, produce ions, and conduct an electrical current. For example, that sodium chloride from last section dissolved in water, this is our dissociation, into Na plus ions and Cl minus ions. This would be a strong electrolyte because it completely dissociates into ions. It would make that light bulb light up. We can also have a weak electrolyte, and a weak electrolyte dissolve mostly as molecules, not ions, produce a few ions, conduct a weak current. Here's an example. HF. We can see that it dissociates into H plus and F minus ions, but it's also going to go backwards to create HF, that molecule. A weak electrolyte forms mostly molecules and a few ions. So we can see in this picture we've got an HF, an HF, an H. We've got 4 HFs and 1 fluoride ion and 1 hydrogen ion. So that would be a weak electrolyte. And then we have non-electrolytes. Non-electrolytes dissolve as molecules, do not produce ions, do not conduct a current. Here we've got CH4O, and in water, we just have CH4O in aqueous solution. It's not separated into ions. This is a molecular compound, and it is not going to light up that light bulb. When looking at strong electrolytes that dissociate completely, we are looking at ions. So examples, ionic compounds are going to be huge, like sodium chloride, potassium bromide, magnesium chloride, sodium nitrate. Bases like sodium hydroxide, potassium hydroxide, acids like hydrochloric acid, hydrobromic acid, nitric acid. Those are all going to be great conductors of electricity. Weak electrolytes like HF, water, ammonia, acetic acid, those are all weak electrolytes. And then a non-electrolyte are going to be all molecular or covalent compounds. Carbon-containing compounds, methanol, C2H6O, ethanol, sucrose, those are all just some examples. But they are molecules, not ions. Here's a sample problem. Indicate whether solutions of each of the following contain only ions, only molecules, or mostly molecules and a few ions. Write the equation for the formation of a solution for each of the following. So pause the video here. For A, we were told Na2SO4, which is sodium sulfate, and we were told that it's a strong electrolyte. So there are ions in the strong electrolyte, Na plus and SO4 with a -2 charge. So we would write that as starting with our solid, dissolving in water, and we are going to break down into, we started with 2 NAs, 2 Na pluses in aqueous solution, and SO4, 2 minus, an aqueous solution. For B, we were told that we had sucrose, a non-electrolyte. So we have sucrose, solid sugar, dissolved in water. We now have sugar that's dissolved, AQ. No ions, it's a non-electrolyte. And for C, acetic acid, we're told that it's a weak electrolyte. So I'm starting with my acetic acid, and a weak electrolyte, we show that it's going back and forth. We have some hydrogen plus ions, we have some acetate ions, but we have a lot of acetic acid in molecular form, giving us mostly molecules and a few ions when it dissolves in water. Take a minute to look over the learning goal for this section. Section 3 is about solubility. You'll be able to define solubility, distinguish between an unsaturated and a saturated solution, and identify an ionic compound as soluble or insoluble. The term solubility is used to describe the amount of a solute that can dissolve in a given amount of solvent. There's lots of factors like the type of solute, the type of solvent, and the temperature that all affect the solubility of the solute. If a solute readily dissolves when added to the solvent, the solution does not contain the maximum amount of solute. We call this an unsaturated solution. A solution that contains all the solute that can dissolve is called a saturated solution. If I put, let's say, salt into water, and just a teaspoon of salt into a large cup of water, and I stir and that salt just dissolves, piece of cake. It's unsaturated. But let's say I keep adding more salt and more salt and more salt, and it keeps dissolving and dissolving and dissolving until it gets to the point where it can't take any more salt. Then we have a saturated solution. Solubility is the maximum amount of solute that dissolves in a specific amount of solvent. It can be expressed as grams of solute per 100 grams of solvent using this formula. Let's say I had 10 grams of salt, which is my solute, in 100 grams of water, and that's the max it can hold. If I put 11 grams of salt in, some would not dissolve. So the solubility is the maximum amount of solute that can dissolve in a certain amount of solvent. Saturated solutions contain the maximum amount of solute that can dissolve. Saturated solutions have undissolved solute at the bottom of the container, and they have equal rates at which the solute dissolves and crystallizes. So if I have solute plus solvent, we can see here that the solute is dissolving and we have a saturated solution, and some solute can crystallize and go back. Additional solute can dissolve if we have an unsaturated solution, but not if we have a saturated solution. A saturated solution is like, nope, I'm full. I have completely dissolved everything I can. I can't take one more speck. It wouldn't dissolve. We can see here our dissolved solute. Let's say that it was, salt, NaCl, that was dissolved in here. And I've got dissolved over on the right side and the left side. This is an unsaturated solution. On the right is a saturated solution. Look, I have crystallization happening because I've got some salt on the bottom, or whatever the solute is on the bottom, that cannot dissolve because it is maxed out. The solubility of most solids is greater as temperature increases. So if I were to put a pot of water on the stove, I could dissolve more salt solute in there as my temperature increases, which means I can have more dissolved solute at a higher temperature. A few substances show little change in solubility at higher temperatures, and a few are less soluble. For example, when you add sugar to iced tea, some undissolved sugar may form on the bottom of the glass. But if you add sugar to hot tea, many teaspoons of sugar are needed before that solid sugar appears on the bottom. Hot tea dissolves more sugar than cold tea does because the solubility of sugar is much greater at a higher temperature. But personally, putting sugar in tea is disgusting. So I stay away from the sugar in the tea. I definitely want unsweetened iced tea. Solubility depends on temperature, increases as temperature increases for most solids, decreases as temperature increases for gases. Let's look at this. This is our solubility and looking at temperature. So as temperature goes to the right, we have greater solubility for that sodium phosphate, greater solubility for potassium nitrate, greater solubility for sodium nitrate and potassium iodide and glucose. The only thing that we didn't see really was salt. And for gases on the right here, we can see as temperature increases, the solubility for gases goes down for oxygen, down for carbon monoxide, down for nitrogen. Henry's law says that when the pressure of a gas above the solution decreases, the solubility of that gas that's in the solution also decreases. Think about a can of pop. I have carbon dioxide that's dissolved in this pop can. That's what we like about it. It gives it the bubbliness. We can see here that we have our gas molecules that are sitting right there, and we have gas molecules in this cola. But then we pop the top and notice that those gas particles are coming out like You hear that psst as soon as you open that can of pop. Those carbon dioxide bubbles are coming out of solution. And if you were to let that can of pop sit out for long enough, all of that carbon dioxide, or a whole lot of it, not all of it, is going to come out and we'll have flat pop. Nobody wants flat pop. Henry's law says that the solubility of a gas in a liquid is directly related to the pressure of that gas above the liquid. And at higher pressures, more gas molecules dissolve in the liquid. Let's look at soluble and insoluble ionic compounds. Ionic compounds that dissolve in water are called soluble salts. So if it dissolves, it is soluble. If it does not dissolve, then it is insoluble. Here are some examples of insoluble compounds. When I have a solid chunk of something formed, in this case cadmium sulfide, iron sulfide, lead iodide, nickel hydroxide, we can see oftentimes they are pretty compounds, but they will not dissolve. They are insoluble. Well, how do you know if something is soluble or insoluble? Well, there's a list of rules. Soluble salts typically contain at least one ion from group 1A, so our lithium, sodium, potassium, or it has NH4 plus, ammonium, or nitrate, or acetate. Those are all soluble compounds. Also, chlorides, bromides, and iodides are usually all soluble, except if it's a chloride, bromide, or iodide with silver, lead, or mercury. And a lot of sulfates, SO4 minuses, are soluble, except barium, lead, calcium, strontium, or mercury. Now, I made a pretty table for you to use. If it's a soluble compound, that means that it will dissolve, so we would write AQ next to it. And if it's an insoluble compound, that means it won't dissolve. That means that it stays in solid form. And so you could look, almost all salts of sodium, potassium, ammonium, nitrates, chlorates, perchlorates, acetates, chloride, bromide, and iodide, except, there's our exceptions. If it is an exception, that means it's insoluble, so it would be solid. Most fluorides are, except, there's a few exceptions, most sulfates are, and there's our exceptions. Now, most carbonates, phosphates, oxalates, chromates, sulfides are not soluble. Now, there are some exceptions. If it was ammonium carbonate, if it was any of those alkali metals in the first group, and barium sulfide is an exception as well. And most hydroxides and oxides are insoluble. Again, there's a few exceptions, but this will be a chart that you can use. You do not need to memorize this. So using those rules, let's look at these compounds. Potassium sulfide. I'm going to go back to this and see which one of these boxes shows me if it's soluble or insoluble. Potassium, here we go. Most potassiums are soluble. Is sulfide an exception? I don't know. Okay, well, K is good here, but let's look up sulfide, sulfide, sulfide. Oh, here we go. Sulfides are usually insoluble, but is potassium an exception? It says salts of ammonium and the alkali metals. Yep, that's an exception. So that would be soluble. Let's look up calcium nitrate. Here in box 1 it says salts of nitrates are soluble and calcium is not an exception. So it would be soluble. Lead chloride. Well, it says most chlorides are soluble. Is lead an exception? Yep, that would be insoluble. Sodium hydroxide. Over here we said most hydroxides are insoluble, but sodium is an alkali metal, so that would be an exception. It would be soluble. Let's look up aluminum phosphate. Right here it says phosphates are insoluble. Is aluminum an exception? Nope. So this phosphate would be insoluble. In medicine, insoluble barium sulfate is used as an opaque substance to enhance X-rays of the gastrointestinal tract. Barium sulfate is so insoluble that it does not dissolve even in gastric fluids. Let's look at barium sulfate. As right here, and most sulfates are soluble, but barium is an exception. Barium sulfate is insoluble. Other ionic barium compounds cannot be used because they would dissolve in water, releasing barium 2+ ions, which is poisonous. So it's got to be barium sulfate. Look at your solubility chart and predict whether the following compounds are soluble in water. Hopefully you got soluble, insoluble, soluble, insoluble. Take a minute to go back and look at your cheat sheet. Hopefully you feel pretty good about that. And if you feel good about that, this next part is going to be a piece of cake. Using our solubility rules, and if it is insoluble, it's a solid. And we call that solid a precipitate. It forms when two solutions that contain soluble reactants are mixed and form a product that is insoluble. Here's an example showing us how. When we have solutions of sodium chloride and silver nitrate, and they are mixed, a white solid forms. Write the ionic and the net ionic equations for the reactions. I'm going to start with NaCl plus AgNO3. Now it says that we have reactants that are soluble. Let's double check. Sodium chloride and silver nitrate. Sodium chloride, here's chlorine, and sodium is not an exception. Yep, sodium chloride is AQ, which means it will dissolve. And silver nitrate, nitrate is right here, and silver is not an exception. So both of those reactants are aqueous, which means that we can dissolve them in water and they will react with one another. Now, this is a double replacement reaction. We know that sodium and silver are going to swap spots. So then I will have sodium with the nitrate, so NaNO3, and then silver chloride, AgCl. Let's look at these products because one of them says a white solid forms. One of these is going to be insoluble. Which one is it? Na and NO3. Both are right here. They're both soluble. That will just dissolve. But let's look at the silver chlorides. Almost all chlorides are soluble. Oop, except silver. That would be insoluble. That is going to be the white precipitate solid that is formed. And we would write this AQ and S. Now it wants the net ionic equations, and we would simply take our reactants that are both aqueous and we split them into their ions. So Ag plus, AQ means it's dissolved, so it's floating around in the water, NO3 minus, and we split apart our Na and our Cl, so we have all of our reactants split apart. And I split apart my product that was AQ, that was soluble. So my Na plus and my NO3 minus, but I don't split apart my insoluble solid silver chloride. From there, the last thing I do is I cross off the spectator ions, is what we call them, which means after I split those apart, there's an NO3 minus on the left and an NO3 minus on the right. And they can just cancel each other out. If they're on the left and the right, get rid of them. Here's an Na plus and there's an Na plus, get rid of them. What am I left with? That is my net ionic equation. I bring down my Ag, I bring down my Cl, and I bring down my solid insoluble compound. And notice, my insoluble was that silver chloride. How do I make silver chloride? Silver plus chlorine. And there we go. That's it. Take a minute to look over this section's learning goal.